So I'm going to talk about something that has concerned me for a long time, and this is the evolution of C++. And basically, what is the essence of C++? What's the key thing that has made it successful and that we must maintain in the future to maintain that success? And then I'm going to talk about the near future. C++11 is still in some people's future, so I don't feel too bad by listing it there. And beyond is, well, beyond. And then I'm going to talk about what we can do now till we get all the goodies that we hope to get over the next few years. First of all, sometimes we forget why it's worth working on programming languages, and that's the applications. I mean, I measure the value of a programming language in what interesting things can be done with it. I'm less interested in the little sort of language technical details. Yeah, they're necessary. I've been doing them for 40 years or thereabouts, but they are not the driving force. They mustn't be the driving force. The driving force is what you do with it. And there's a few things there. I mean, there's a Lego lady up there. I mean, guess what they use for design and the manufacture. And there's the CERN cyclotron. I'm really happy that C++ was used in a major way for a lot of those experiments, including finding the Higgs boson. We've done one little bit for basic science and mankind there, and so on. And I have some C++ applications up there. If you find my talk getting into a topic that you've heard several times before, you can always look at the pictures and try and imagine what it has to do with C++. They've all got something to do with C++. There's more applications there. If you're into rocket science or mining or astronomy, this is C++ is a good way of getting there. And there's more of this. I'd like to point out that I got into this through distributed systems, and there's a distributed system with wheels, the red one. This all started in '79, back in the dark ages, in the previous millennium, at Bell Labs. I wanted to build something. I couldn't quite decide whether it was a Unix cluster or a multiprocessor, but definitely I wanted to split C++ split systems to run on several processors, communicating in some way. And for that, I needed two things. I needed something that was really good at classical systems programming. Write a scheduler, write a memory manager, write a network driver. And I needed something where I could say, this is one part of the software, and that's another part of the software, and here is how they communicate at a reasonably high level. And there wasn't a language that could do both at the time. And I needed both, so the basic idea was simple. You take similar as classes and put them into C, make them fast enough to be useful for heavy-duty systems programming, and that would solve my particular problem. And I don't really like to solve particular problems, because after a couple of years, the particular problem I deal with now is no longer the right problem. The problem has mutated, the world has mutated, our understanding has changed. So you try and generalize, so you solve a class of problems surrounding the real solid problem that drives the application. So I went for generality. And no, I never got to write that system. My friends started using C with classes, that it was called, and I got sucked into improving C with classes, became C++. I helped a lot of people, maybe 10 projects a year for 10 years or something like that. So this thing was driven by real problems, a lot of them, a very diverse set of problems, and that was how it got got going. And from that, we can sort of generalize a bit. When I stepped back, I realized that what I had taken was basically 2 lines of development of programming languages. And you may all know this, though I doubt it. I know my students don't know all of this. I know that the average conference doesn't know all of this. Back in the really dark ages, there's a line of development going from assembler through BCPL to C. And there was, I think I knew at least 20 languages down here when I did it. The point is, you have to squeeze every single byte and every single cycle out of the hardware. And that was essential. That was the way you wrote code. And if you're doing things like high performance or low latency code, you're still doing something like that. But down by the hardware, it's really unpleasant. Mistakes have bad effects. There's not much support. And mistakes at the lowest level can be disastrous. And so people started looking for a higher level of programming. And what the Fortran guys did there, there's backers, was to lift the level of programming to something fit for humans. Those particular humans were scientists and engineers doing linear algebra, that kind of stuff. And as soon as that worked, finally people could write in the terms they were thinking about, rather than in the bits and bytes. Then everybody wanted one. We got COBOL and about 200 other languages. That meant that you couldn't communicate. So if I had a Fortran program and a COBOL program, they didn't work well together. If I had a problem that requires both, it was difficult. And that's where Christian Nygaard and Simula and object-oriented programming comes into the picture. It allows us, instead of having domain-specific concepts, domain-specific facilities in the language, we had instead a set of mechanisms for abstracting things. You can build your own abstractions. If you, in a language like Simula or anything that comes after, wants a nice record concept for business applications, you build it. If you want a matrix abstraction, a vector abstraction, you build it. And since they're in a common language, has a common foundation, they can interoperate. That's important. And so what I did was to take the ideas from the top level and the ideas from the bottom level and put them into C++, where you could afford to do both. That was the idea. And from there, a lot of things happened. So I can describe C++ in 2 lines. First of all, there's a zero overhead abstraction. You have classes, inheritance, generic programming, and such. That's the upper line on that language diagram. Comes from from Simula originally, where it most certainly wasn't zero overhead. There was all kinds of memory and time overheads involved. And in the future, I want more of that and better of that. Similarly, at the bottom, we have the direct map to the hardware just basically use the hardware optimally. Initially, it came from C, and in the future, I'd like to extend this to use modern hardware better. To be a little bit more concrete, the map to the hardware comes by having the operations in the language mapped directly to the instructions on the machine. So if you do an integer add, you get what the integer add is on the machine. And this is good. You can get maximal use of the hardware. On the other hand, it may not have quite the right abstractions for you. Like if you take a modular of a negative number, it may or may not, on that machine, give you what you expect. So you can make the language more beautiful by lifting the level all the time, and that costs you something, possibly a factor of 2. That's distributed fat. Or you can let people have to know what the machine is and write that if statement for a negative modulo, if that's what you need. When you go to use the memory, you have some values that maps into what's basically in the machine, int, doubles, complex as 2 doubles and such. You can build simple values like that, and then you can build things that can vary, handles and values. That's vectors, strings, thread, matrices, all that kind of good stuff. And the object can be composed by simple concatenation. You stick things of the same type next to each other and you get an array. You stick things of potentially different type next to each other and you have a struct, and or a class if you call it. So you get that. And basically this is dead simple. And it's the simplicity that matters here. This allows you to use hardware optimally. If it had been more clever, if it's been more complicated, it would not have lasted since basically Dennis came up with it in '72. This has served us very, very well. Now, zero overhead abstraction takes that one level up. You build things out of what the machine provides. What you don't use, you don't pay for, and what you do use, you couldn't be able to hand code better using the lower level language features. That's known as the zero overhead principle. I documented it a few times, including in Design Evolution of C++, and that's one of the design rules for C++ that has kept us reasonably sane over the years. And basically, there's all of these things that can be done. Notice that if you take something really simple, like a point, two integers next to each other, or three if it's 3D, or a complex number, you just stick them next to each other. There's no overhead. There's no sort of really helpful thing like putting the time of day into every object so that you know when it was created. There's languages that do that for you. C++ doesn't do things for you. If you want it done, you can do it, put it in a library. So you can also get a standard object-oriented object here. You have some values here, just like those up there. And then you have the functions that can be virtual so that you can override them and give them a new meaning. And there's some overhead by putting it over on the free store. There's a free store header. If you want that, you can get it. That's very easy. It's just a class with a virtual function. But if you don't need it, if you don't want it, you are back to the basic things again. We don't give this kind of more advanced stuff in every case, because that would cost you what you didn't. And this again is why you can use the abstraction mechanisms in high performance code, low latency code, basic stuff near the hardware. You can stick the top example there on the stack, for instance, which is often important. It is not like in many languages derived from Simula, where if you have a user-defined type, it object has to be on the free store, the dynamic store. And so one thing we can observe is that the C++ machine model is itself an abstraction. Hardware in those days in '72 didn't all look like that, a simple string of objects put next to each other, segments of that, and that model. It itself was an abstraction of many machine architectures, and over the next 40 years, the machine architectures have changed quite a lot. So there's a layer below the C sort of basic memory model, machine model, down to the hardware, and of course the hardware itself in this is an abstraction. If you run on an 86 machine, the first layer in hardware translate into something that's more like MIPS instructions, which translate. Eventually we get down to sort of device physics or atoms. So basically it's abstractions all the way down. The crucial abstraction is the C machine model, and we're working on that in the committee to make that better. And I hope we'll come up with something that's not too complicated. Just now it's very complicated, but most of us most of the time don't have to think about it. We can think about this, because that's a good intermediate abstraction. So one thing that I've been looking at since basically the second week of development of C++ is how do you do resource management? And so resource is anything that has to be acquired and then given back. And it's obvious, it was obvious then and it's even more obvious now, that if you have to remember to give something back, you better not have too much of it. If you have 10 or 100 objects and you have to give them back to some manager, It could be memory locks, file handles, sockets, thread handles. We'll get it right, 10 to 100. Okay, 1 million objects, you're going to forget it. So we need to automate this. And that's what's done in C++. And we have vector of n integers and the file stream. They acquire something, and at the there is where the magic happens. The destructors fire, and we're cleaned up. And basically, we don't want leaks. We want to minimize resource retention. Sometimes holding on to a resource for a long time is just as bad as leaking it. Depends on the time scale of things. And as you all know, this is the way it's done. You have a user-defined type here, a vector of elements. They're called classes, by the way, because Christian Nygaard, you saw there, wasn't a computer scientist, he was a mathematician, and he knew about classes. Types were sort of a later invention. And so there's two constructors and a destructor that handles it. Constructors acquire resources as necessary, creates the environment that member functions work in, as I expressed it in 80. And the destructor reverses that action, releases everything. And then there's the implementation, which is the next level down in abstraction. Vector is just a standard example. It has the constructor-destructor pattern here. It has operations, and it is built out of further abstractions. And you can look at all of these things, spaceships, engines, whatever. They're using this kind of thing, abstractions all the way down, turtles all the way down, however you want to express it. And it's not just memory. I'd like to emphasize it's not just memory. The fastest way I know of crashing a machine is to open too many files. It's much faster than trying to use all the memory, at least with normal mistakes. So all the standard library built on this, and not just the memory, thread, log guards, file streams, and the shared pointers. So that's the way it works. Now, I'm talking about a programming language here, and I'll just get back to the sort of almost first slide about applications. What we are talking about is very often sort of language features. That's one part of a language, but it's the crucial thing we talk about. But there's so many other things that happens. I like to think about stability and evolution. A lot of the applications we have last for decades. So people want new things, people want fancy new things, but by and large, if I come and tell you that I will give you what you really, really want, but I'm going to take away this major feature of the language, you're going to scream, "Don't break my code." So we have to have stability over decades, but we mustn't just stand still. The world changes, we change, and so the language has to keep up. So we have to balance stability of evolution and the rate of evolution and things like that. And there's tool chains, teaching issues, technical community. I should thank Jens Weller for doing the Meeting C++, and especially for that list he makes every month of other user communities out in the world, because over the years the C++ community has been lousy at community building, and this is very important and good here. I'm interested in concise expression of ideas, coherence is important, da-da-da-da-da-da. I can't talk about all of this. This is just one talk. But for every talk you hear, you can think about how it contributes to the bigger picture, which is not just characters on a screen. And one of the things that I realized early on is that being the best of one or two things isn't sufficient for success. A language to be used has to be good at everything for a given project, for a given domain. You can't be good at everything, but you have to be useful, you have to be good enough for everything in a given domain. The problem is you do not know what good enough is or what everything is. So you're designing sort of in the sort of flying blind to some extent. You have a lot of experience, and I'm trying to rely on generalization. Go from concrete examples then generalize. And without damaging the core, we still have to have stability, you still have to performance. So we shouldn't obsess too much about a detail. So C++'s role in all of this is to try and be a general purpose programming language. That is, a language that is not aimed as a single, well-defined application domain. If you know exactly a limited domain, you can do better. But C++ is for where you can't do that. And so my aim, as far as I see it, is C++ should help build dependable and affordable software. You need both of it. Affordable is important. And I hate choosing between efficient and elegant. One of the problems in the early days was you could get languages that allowed you to write elegant code, like Simula. And you could have languages that allowed you to write efficient code, like BCPL. And having to do that choice is horrible. And so we try to extend the set of problems for which C++ can deliver elegant and efficient programs. And lightweight abstractions is the key. I want to be able to build a complex number that competes with Fortran complex. You have to compete with the gold standard in any field. I'd like to build points that can work for graphics and for, say, fluid dynamic simulations. It's things where it matters. And resource-constrained applications, these are the resources that I talked about before, that you acquire and release, but also resources that you consume unconditionally, time and power. That's useful. And then where this comes in is building software infrastructure. And our technique is the usual here. And then I'd like to emphasize, no language is perfect. I'm not telling you C++ is perfect. If somebody comes and tells you they have a perfect language, it's either a salesman or a fool, and probably both. So here is the dragon. If you have ever read Alejo and others' book on compiler design, you will know that the knight armed with the weapons of computer science is slaying the dragon of complexity. Well, sometimes the dragon wins. And so I've given the caveat. I like C++. It's my best tool for a lot of things, but we can make it even better. And I wasn't saying it was perfect. So the evolution has happened over the years. C++ 98 is a solid workhorse that a lot of people know, and you know a lot of people are still stuck with it, or still stuck with the mentality that C++ is C++ 98. Or even there's a lot of people, unfortunately a lot of them in education, that really think C++ is sort of what it was in about 88, 10 years before the first standard. C++ 11 was a major improvement. Gave us support for concurrency, regular expressions, lambdas, all kinds of good. We can actually write much nicer code today, and we can write much code that runs much faster. This has been proven again and again in real production software. There are people that are nervous and saying, oh, we don't want to use these new features because they're complicated and probably expensive. No. If you move to more modern programming styles using the new features, by and large, people find that their code speeds up. C++ 14 was designed to complete C++ 11, and it's currently shipping by the major compilers and also other compilers that are usually built on the EGG front end. And C++ 17 continues the, what's it called? The development from C++ 14, there's something for everybody there. Usually some little things. There's nothing that will change the way you write code and think about code the way C++ 11 did. That'll have to wait. And I'd like to remind you that languages and standards don't write themselves. Here's the C++ Standards Committee in Madrid celebrating. They've just voted out C++ 11. So there is a couple of trends here. We try and handle more advanced things, but we try also to make it easier to use things. So one of my main concerns is that C++ tends to get too expert-friendly. And by adding things that makes things easier to use and to generalize, we can actually make it simpler again. And I'll claim I can write simpler code in C++ 11 than I can in C++ 98. I'll show you an example. But here's a little example. In 72, Dennis designed the C for loop. You have a variable, you have something that's supposedly an initialization, something that's supposedly a test, and then incrementing a loop variable and you do something. And that's the way we did it for a while. I got tired by having to first define a variable and then assign to it later. I find that correlates with bugs and think it's verbose and ugly, and if it's what you need, that's good, but quite often you can do the simpler version of doing this. In 11, we got this. Basically, for all x in V, assign 0 to x. This is a reference, so the assignment doesn't go to a copy, it goes to the object itself. Auto is because we realized that a lot of the time the compiler actually knows the type. I mean, for all x in V, the x are the elements of V. The compiler knows what the elements of V is, so type is, so we can just deduce it. So this here is shorter, just as fast as the old versions. It works really beautiful for the simple cases. If you want to do really dirty tricks with your loop variables, feel free. You will find that sometimes you make mistakes, like I would say everybody here has made one of the two mistakes in that example at some point or other. If not, they have friends that did. And I'm very happy to avoid it by using the new thing. Simplifying things is necessary because since we can't clean up C++ by throwing away something useless, for starters, we would never be able to agree on what was useless. The language will grow, and in that sense be more complex. But we can simplify the use of it so that most of the time we don't have to fiddle with the error-prone things. Another theme here we have is concise expression of ideas. We would like not to repeat ourselves too much or to be too verbose. The range for loop is an example. And here's a lambda. A sort function takes two things, a collection of data and a criteria for comparing elements. And here it says, well, how do we compare the elements? Well, we take two elements and we compare them with greater than. That way we get sort in descending order instead of ascending. Basically, that's a fairly concise way. I was a bit worried about lambdas. I was one of the people who was designing it, but I was worried about overuse. Because one of the rules of the game that you learn is that every new feature will be overused and misused. You cannot avoid that. I learned that the hard way. So I was a bit worried, and I find that in real production code, you can actually get cleaner code sometimes, if you use it well, using this. And one of my ground rules is that it's more important to enable good programming than to eliminate bad programming. There are other ways of attacking the bad programming. I'll get to that. And here's sort of a standard reactive GUI kind of thing. You want an action, you give it some context, and then you specify what's being done. So we're working on simplicity and concise expression. That's important. And so I'm not going to go through a list. There's nothing as boring as a talk that's just a list of features. You know, the web is really good at this. Look up C++ 11 in Wikipedia, and you will find long explanations of every line on this slide. I'm not going through it. And by the way, if you want an overview of modern C++, I can recommend this book. I wrote it, so take for the recommendation for what it's worth. But the point is that it covers C++ at a given level of abstraction, but it covers everything in 180 pages. And by the way, you don't have to read it in Chinese. It's there in English too. So let me show you a piece of C++. I think, yes, that's 11, but since it's also 14 and it's also 17, we're interested in stability. So here, I want to find all elements in a container of V that matches, every element in the container C that matches the element V. And I want to get back the pointers to all of these elements. And this is easily written, right? We take an empty vector of pointers. We go through all the elements for every x in C. If x equals V, we put it on the back of the vector it grows, and we return it. And we can test it. Here's a little test program. You can see a string as a container of characters if you feel like it. So for all A's in M, in other words, that, and that, I should get a pointer back. And then I can loop through it again for all those pointers, see if the pointer points to an A, and if not, somebody screwed up badly. Now, the main difference between C++ 98 and C++ 11 is what's not in this slide. Notice that I'm returning a vector of pointers by value. Here it's 4 pointers, so it's 4 times, say, 4 or 8. It's not too bad. But I could feed this one a megabyte of data and get, or gigabyte, and I can get back a megabyte of pointers. Even modern hardware can feel that. It's not good. However, one of the things we've figured out, and that's built into C++ 11, is move semantics. Right? If I have something here and I want it over there, well, I put it over there, right? Only a computer scientist would make a copy and then destroy the original. So we don't. We sort of steal the representation. If you don't know about move semantic, look it up. Because this is why this slide does not allocate some stuff on the free store, pass out a pointer, leaving the user code to free the result. There's not even a smart pointer here. It's gone. The complexity is lowered, and let alone the people stuck in the mid-90s that would have a class hierarchy or something or other here. It's not there. It's just much simpler. It may be that the syntax is unusual for some people, but you get used to it. There's roughly a one-to-one correspondence between the characters in the program and the stuff that is being done. That's one of my definitions of elegance. That is one-to-one correspondence between the way I think and the way I write about it. Back to this zero overhead. There is a way you can do better than zero overhead. You can move computation from runtime to compile time, so that when you run something later 1,000,000 times, you have saved yourself a lot of bother at the cost of some compile time. So constexpr brings type-safe programming to compile time. So basically you compute the answer. There's a lot of application areas where people compute an answer on a doodle pad next to the screen and then type in a magic number. 2 years later, that magic number may be all wrong, but or maybe you hit the wrong key on the calculator or something. It's not so good. It is much better for maintainability that you compute your final things at compile time out of the things that are stable, like the size of an integer and such. Here's an example that was requested by somebody in the Japanese embedded systems industry. So this is a real example. I got it in my mail maybe 10 years ago. And finally we've got it. If I say constexpr to a function, the compiler checks that the function can be evaluated at compile time if you give it constant expressions. If you give it variables, it'll have to do it at runtime, of course, because, well, The value of a variable is not known as compile time. But if I give it a 9, it can go and calculate 3. And so 3 will be put into memory. If you want to guarantee compile time evaluation, you say const expert to the variable that, well, it'll be a constant, that you want evaluated, so that works. And so this works nicely for built-in types, integers, float and such. But we can do it for user-defined types. The point is that people often computed things at compile time, and very often they did it with macros and such stuff. That becomes typeless, or at least type impoverished. We can do it with higher levels. So here is a library for sort of day of the month kind of stuff. So I take June the 21st, 2006, and I want to know which weekday it is, and I write it out. That's fine. But I can do it at compile time too. I want to assert. Static assert is a C++ 11 feature that's very useful for making assertions about what should be true always in the compiler. So the weekday of June the 21st, 2016 is Tuesday. The program will not compile unless that's true. It was true when I checked it, and I don't think it has changed. So basically, this trend of doing small things that are generally useful is carrying on into C++ 17. It was, I say, approved last week. Well, there's another meeting, but I'm pretty sure this will hold now. I couldn't have been so sure last week. But anyway, we're going to get this, all kinds of good stuff here. Variants, any optional. That's my favorite here. Structured bindings, I'll mention in a second. There's structural bindings. It's a feature from C++ 11. I believe it is in the latest version of Clang, whether shipping or not, correct? Oh, it'll be there soon. I have seen some people working, but that was not the shipping version. So basically, we find that there's a lot of code out there that uses pairs and tuples and basically returning more than one value. An example is insert into a standard map. It returns a pair of values. So nowadays, we have to write pair of something, get this, and then refer to first and second for the pair. This one simply can break out a sort of a struct like that. So it returns an iterator and a success indicator. So we call them iterator and success indicator, and we can write this. This makes a certain kind of programming, which is not uncommon, somewhat more convenient. And the real kicker comes in when you combine it with the range for loop. So for every element in my map, take its key value pair. My maps has a key value pair, and you can write it out. So again, working in combination is important for simplicity, and this feature is very nice. Now, going from some fairly concrete stuff and things that fit on a slide, I'd like to talk a little bit about philosophy. And there's two quotations here. This is Goethe, dream no little dreams, and Voltaire, the best is the enemy of the good. I would like C++ code to be type and resource safe, completely, guaranteed, as fast and faster than anything else. That is, any other way of doing C++, any other language. I want it to be good at modern hardware, really good, not just blah blah arm waving good. And I want the compilation to be catch more errors and go faster. These are not modest aims. If we get this, all our lives will be notably better, and I hope that will give us notably better applications built out of it. And I don't want to just dream. Then you would violate this. Anybody can dream, anybody can write what they want. We have to work on it, so we're going to see what we're doing about it. I'll take some philosophy here more. When we are moving forward with a language design, or a library design, or an application, we will make mistakes. This is known. So let's make them early so we can fix them. Integrate early is what we do in projects to figure out where the errors are, so that we can test. We can start testing. As soon as we have integration, we can test. Before that, we are philosophizing. I would like to maximize successes rather than minimizing failures. If you have the lowest number of failures, or if you try for 0 failure, you will not get very much done. Basically, you could wait forever to try and avoid errors, but that doesn't help the users. And any change carries a risk, and doing nothing is also risky. Yeah, we'll screw up somehow, but if the alternative is to write in straight C, we can probably do better than that. And, on average, we have succeeded over the years, so we should move forward with confidence. Not confidence that we will not make errors, because we will, but confidence that we can detect the worst errors and fix them before they hit the user community. I find that this is not new philosophy. So here's this: it's more important to support good programming than to prevent bad programming. That's a straight quote from DNA, when I, in '94, had to philosophize about what C++'s philosophy was, why it was successful and such. And one thing we have to try and avoid is to confuse familiarity with simplicity. People look at a piece of old code, ugly, complicated old code, and they say, that's fine, I understand this. And you see something new that's half the size, but it's new, so it's complicated, it's difficult, it must be slow. And we have to try and overcome this and evaluate things relative to what there really is there, what it really is that will affect the future. And the reason we have to philosophize rather than just look at language design issues, language technical issues, is that to get a coherent language, you need to have a set of criteria that in some sense is outside the language. It's something that talks about how the language is to be used, what are the fundamental assumptions you're dealing with. And a language is more than a collection of features. If every feature is good, a language can still be a mess. If you take everything and throw it in, kitchen sink or not, if they don't fit together, there's a problem. And every feature carries a cost. So if we take features and add them, and every one of them is good, the net effect can be bad. I have given this talk to people that are not C++ experts, and they look at those lists for C++ 14, C++ 17. They go, it's complicated, it's too difficult. A textbook writer says, I can't write a textbook finding all of that. So we should be a bit constrained about features that just helps a few people. And the language design rules are mostly non-technical. I'll go quickly through them. But we need the philosophy to get a coherent language and to maintain a direction towards a coherent language. It's hard to do it just at the technical level. And I think this is actually a major problem. We need an articulated set of design principles and current aims. Design principles in general, current aims is where do we go next. And WG21 doesn't have it. And that shows. That's one of the reasons I worry, one of the reasons I talk about evolution just now. I think we are at a point where we could make mistakes. So let's go back in time, take the time machine back 20 some years. I was asked by the ACM History of Programming Languages conference to write up the history of C++. And there was a set of questions, and the main question was, why did it succeed? I mean, it was supposed to be stillborn. It had no resources, used the wrong principles. Everybody knew that languages should look like either Ada or Smalltalk or one of the other 20 languages. C++ wasn't fashionable, never was. So I had to explain this, and so I came up with a lot of details and then some practical things. driven by real problems. I was really, really worried about language theory and theory papers that may solve a problem, may have the beautiful solution, but it may not solve the real problem. Don't wait for perfection. There's so many languages that had been in development for 10 years and were still not ready for prime time. Let's get it out there, let it hit real users and see what happens. Oh yeah, now. I served my first user after 6 months, commercial release after 5 years. I was in a hurry. I'm still in a hurry. Okay, that one we failed at. It's not that obvious anymore. Transition path. You have to be able to grow from where you are to where you go, and it's not a complete system. Let's see, what have we got there? Make it affordable. This is the closest. There's a couple of things that add up to the zero overhead principle. Say what you mean, direct expression of ideas. I think I could write this list better today, but it would not be radically different. And if you look up in the design and evolution of C++, you see each of these lines have a fairly large paragraph, 20 lines, 40 lines, explaining what I really mean. This is the first level. So I'm more... And here it is, more important to allow useful features than to prevent every misuse. That one has never been popular. I mean, all the Viet languages are designed to stop you from making mistakes. The problem is who defines what is a mistake. I was of the opinion that I wouldn't let Niklaus Viet do that for me. And I'm sure Niklaus Viet didn't want me to define it for him. So the conclusion is that we should try hard to identify what actually does good and then use other means to catch mistakes. Oh, I love the static type system, still does. It's been improving over the years, like we have move operations now. Provide us good support for user-defined types and built-in types. We are getting closer. Locality is good. It's good for performance, it's good for maintainability, all kinds of stuff. Syntax matters in the weirdest way. And here, I'm still after the preprocessor usage. I would like to get rid of the preprocessor. It's not going to happen this decade. I hope it doesn't last till the end of the decade, the end of the millennium or something. But we're getting closer. You can write your code better without macros, but there's all of this old stuff. When we come to modules, you'll see where I would like to see severe limits on preprocessor usage, if that's what you want. Low-level things, there's some here. We can go further with this. Let's look ahead. High-level aims for C++ 14 and beyond, 17 and beyond. Improve the support for large-scale dependable software. That's good applications, but it's not amateur stuff, really. I didn't say the easiest way of writing a web app. That's somebody else's domain. High-level concurrency models. There are so much concurrency going on, and no one way can be simple for everything. So if we look at the ideal of simplicity, make simple things simple, we actually need multiple levels, multiple concurrency models for different uses so that these uses can be reasonably simple. If you are dealing with threads and locks and delayed and various memory models, you're never going to get it simple, and you're basically not going to get it right on the large scale. So we have to do that and simplify core language use and address major sources of errors. We have to simplify. Again, don't break my code and don't make it slower. So we can't abandon the past, and we can't just sit still. And beware of small feature creep, because it scares people a lot when I go and talk to people in sort of user community, small companies and such. And if you mention professors, it's even more. So there was my top 10 for 17, done 2 years earlier. Unfortunately, we didn't get this. We got a little bit of the vocabulary type and a few vector algorithms. So unfortunately, we didn't get any of these. The committee did not focus on these. They spread their energies out over all of the projects so that we didn't get any of them just now. That's unfortunate. So let's see what we can do. First of all, if you're not writing in C++ 14, try to get there. The hard thing is to get from 98 to 11. Getting from 11 to 14 is usually easier. I've seen a lot of projects in development, in real production, that has managed to do this. So get to 11 and then to 14. C++ 17 has lots of minor improvements. There's a little bit for everybody. It's probably not all for one person in particular, but I am convinced that there's nobody in this room that will not benefit from something or other. They may have to look hard to find it, but it's there, so look. And I hope for rapid implementation compliance. I'm not very trusting about implementation compliance speeds, but I don't have to be because most of it is there already. If it's not in the shipping versions, it's in the experimental versions, so I'm actually confident that 17 will be shipping in 17. Modular, so 99.99% will do it. And then you can try out the technical specifications that are there or coming, concepts, ranges, networking, coroutines, modules. There are quite a lot of them. And then I'm going to mention the core guidelines. That's also what I'm going to be talking about when I'm trying to do a Peter Sommerlath imitation after lunch. This will be interesting because I did not know about it till 10 minutes before this talk. Anyway, I would rather have listened to Peter Sommerlath, but that's not possible. So I'm going to talk about the guidelines also. So let's look at the concepts. So I think generic programming should be as close to ordinary programming, non-generic programming, as possible. So here's what we learned sort of on the first day of how to write code. Here's a function, it's a square root function, you feed it a double and you get a double back, fine. If everything's fine, the double that comes back will be the square root of what you fed it. So if you feed it a double, you get the square root back, fine. You feed it something that isn't a double, and the compiler says, well, you messed up. That vector of strings is not a double. And that we got used to that on the first day or two. I mean, we may have been a bit disappointed because most people write some code and they know it's right, and why does the compiler complain? But the compiler is your best friend and it gives a good error message, and after a while get used to it. Now with templates we write something rather different. I want a sort function that can sort anything that's sortable. And what I have to do is I have to say for every type T, do something. And the interface here that says what it means to be sortable is in the manual. But the compiler doesn't read the manual. The compiler reads the source text to see what you actually used. So we come down here and we give it something, a vector of string, yeah, it's sortable, fine. You give it something that's not sortable. This is not what the compiler says today. This is a simple example. Once you start nesting these things and calling generic functions from generic functions, you can get spectacularly bad error messages, even from the best compilers. I had a case a year ago. I was making a slight mistake in a 5-line program. And I was running, it was a Cygwin window on Windows, and the first of the error messages didn't fit into the window. It just blew it. Okay, well, this is an old compiler. Let me get a new one from a different supplier and get better error messages. The same thing happened again. But the thing I could see The one was saying there was bugs in chrono, and the other one had some complaints about something completely different. I was totally lost. Thousands of lines. Okay, this is a problem. The real problem, of course, is that you have to go in and look at the implementation to figure out what was required. There is no decent interface here for all type T. I don't want to sort all type T's. I don't want to sort doubles. Okay, so what I want and what I can get if I download the latest GCC compiler is I want to say sort of anything that's sortable, and we can define what sortable means. You can actually look it up in the standard. A sortable is something that has a beginning and an end. It's something that is a sequence. It is something where the sequence provides random access, and it's something where the member type has a less than. Okay, the compiler does not read manuals, but that's what it means. So if I take this one, everything works. If I give it a double, it actually gives an error message. GCC 6.2, it says D is not a sortable. It wouldn't say container. It will say it does not meet the sortable criteria. And if you're lucky, it also tells you why not. And it doesn't bloat with it. That's my ideal. And this you get for something called concepts. They are compile time predicates. So you basically can ask a type, do you have this property? You can ask a collection of types whether you collectively have the property. So if you want to see what's mergeable, you have to say there's these two input types, and there's these two types, and the first two has to be input iterators of, is it forward iterators? And the third one has to be a output iterator, and the member types has to match things. So this is not just a kind of type. It is a general predicate over a set of concepts. And you can say that a type has to be sortable, and the the element has to be of the sortable type. So we can try a vector of doubles, a list of ints, sort the vector, it's okay. Sort the list, you get an error. You get an error right at this point, not late at instantiation time, not at build time long after you saw this one go. You get it right here, and that is the actual error message from when I ran it 2 years ago. So this is not really new. And you can get more information. And if you actually really wanted to implement sorting on lists, I wouldn't recommend it, but if you need to, you could simply say we have the sort for sortables. We define a sequence, which is something that doesn't offer random access, but it does offer less than in the way I defined it. So what you do is you just copy the sequence over into a vector, sort it, and copy it back again. And now we can sort from sortables, and we can sort from sequence. Notice that I don't have to say what the relationship between sequence and sortable is. The compiler can figure this out. After all, if you look at it, sequence is defined as just the same as sortable, except that it doesn't require you to provide random access. Another thing that's major and hopefully coming up is modules. Today, we have a very weak notion of modules that go back to about 74. We include something, and we include something more, and then we use it. This is fine. It has served us for 30 or 40 years, depending on how you count. But have a look at facts. Here are the number of bytes I typed, 176. Once the preprocessor has seen it, in GCC you get 400 kilobytes. Clang, being more modern, give you 1.2 megabytes. Similarly with Visual C++. Now, remember, your compiler is really, really good, because most of the time you don't actually notice a major delay for a little program like that. However, if the program is a little bit bigger and there's a few more of these, you can start getting real problems. And now you do it 100 times because there are important headers in different a part of the system. It really hurts. So we need to do something else. We want code hygiene, we want fast compilation, so we provide a module system that actually has import statements, so we import these things. The difference here from there is there we import a bunch of characters, we include a bunch of characters, and the compiler has to work through it again. Here we have something that is compiled once, we have a precompiled version that you can't modify. And so it's far less information coming in, and the code looks the same. And we should get major improvements here. Writing a module is easy. You have a module, we have an export, things that can be seen from outside the modules, and that's probably it. Huh? Didn't even use duct tape. So basically that's where I hope we'll be going. And now my dilemma here. Here is a nice program using 3 features I really like and I could use to improve my everyday programming. So I am importing I/O streams. I'm defining a module which is a map printer, which I like to give to you. I export the print map operation. This is specified to require something that is printable of a key type and a value type. They have to be printable. And then I want to do a range for loop, breaking out the key and value pair like this. Nice little program, right? It all works. That is, the structured bindings work in Clang, the modules work in Visual Studio, and the concept work in GCC. I hope to be able to run this program sometime in the not too distant future. Next year would be fine. This year is unrealistic, unfortunately. If we had decided this was important to get to run, we could have decided that last year, but we didn't. So, again, remind you, these things don't write themselves. There's lots and lots of people involved. This is just a bunch of the people that has been working on some of these features. Herb, I think, was the one that started structural bindings. Gabby Dos Reis is the main worker on modules for the moment. Andrew Sutton, Gabby and I worked on concepts for the last many years, and so on. So now I'll switch from language design, language evolution, standardization to how do we actually use this. Last year, I started a project at Morgan Stanley trying to figure out how to get people to use modern C++ for whatever definitions of modern. Something that used C++ 14 well. And in fact, I was defining my job as to figure out what should your code look like in about 5 years if you could get your druthers. And if you think the answer is just what I write now, you lack imagination. We can do much better in 5 years. We can do much better than anything I showed here, I hope. I mean, we have a whole standard coming before 5 years' time, right? So I was trying to design some guidelines. And there's lots and lots of rule sets for languages, but I found they were too short and too conservative, very often written to ensure that you could still use, say, GCC 3.4, and therefore banning all modern programming things. So let's be idealistic. What should the code look like? Secondly, you don't get coherence by just writing a lot of rules. So we separate into a set of sort of philosophical rules They're primarily for humans. It's so that you can sort of grasp what is supposed to go on, express ideas directly in code. We can discuss what that is, but if I want a matrix, I want a matrix. I don't want an array of arrays with some sizes implicit. Write in ISO standard C++. No, I don't like proprietary extensions, and I don't like to invent new things just for guidelines, and so express intent. Obviously, the compiler cannot test these things. I mean, it doesn't know what your intent is. You don't know if your ideas are expressed directly. So this is a framework for making rules. There are some things that are language technical almost. Don't leak any resource. This is still C++. Don't waste time or space. The zero overhead principle still holds, and it's built into the sort of philosophical guidelines for that are there. And then we have the more concrete ones. They're sort of the path through the wilderness. We want to have them provide enforcement. We want tools that can check this, and we want to write the rules so that they can be checkable. So these are primarily for tools and allow specific feedback. And it will help unify style. That in itself is an advantage in some cases. They are neither minimal nor orthogonal. There's a lot of them. And this project has a lot of, people involved. It was started by me, then friends at Microsoft, Herb Sotter, Gabby Strays got involved, then some people at CERN, then some people at Red Hat. We get a fair amount of input from the Clang community also. This is quite ambitious. And it's not total vaporware. Here is an output from the checker that the Microsoft folks ship with their Visual Studio. There's also a little bit of checking, less, that you can find in Clang Tidy. I mean, we're trying to be really broad. If this only worked on one implementation, I wouldn't take part. So when did you last hear of some people from GCC and Microsoft sit together and design something? The world is changing. We're making progress. So here is an example. This is a checker written by Neil McIntosh at Microsoft. And here is this thing. You can probably not read it down back there, but basically I'm creating a variable of type S42. This is one of my test programs. S42 takes 2 pointers to integers. Simple. And I give it 2 pointers to integers, p, so int star, and that int, which value is 7, is an int star. That works. This is good legal C++. The checker notices that ownership was lost. We don't know. There's no guarantee that this pointer here, which comes from there, will be deleted. So you have a new in the code and no matching delete. And it gets violated. All checking, by the way, is local. So this has to scale to large programs. This has been tried for small programs, test programs, 1,000-line programs. We're trying it on million-lines programs, but I can't claim success yet. But it's not total vaporware. So I would like to write type and resource safe C++. I have a paper arguing that we can do it. No leaks, no memory corruption, no garbage collector, no limitations in expressibility. That's important. If I can stop you from writing anything useful, I can guarantee you don't make any mistakes. Okay? It's easy enough. You need this one too. No performance degradation, still C++, has to run fast. It is not a set of rules that says, use this bloated library, or use these slow techniques. In particular, I don't want shared pointers all over the place. I want shared pointers only if you need to share ownership. And I want it tool enforced. I gave you the caveat. So this is, of course, one of the golden holy grails of programming. So it's not unambitious. You can find it. It's on GitHub, and work started there. Okay, so I reached the end here. I think C++ is still true to its principles, but we have to articulate those principles and make sure that people who's only been here for 10 years have actually heard them. There's a lot of people who have never heard of design and evolution of C++ and couldn't possibly imagine it would be relevant. And we need to focus on real problems here. So this is the fundamental principles as I see them. We're working, we are improving. We can improve further without changing the language, without using new facilities. We can move to better use, and you can experiment with all these new features, and then you can support the standardization implementation efforts. There's a lot of stuff going on. In particular, there's a contract proposal in the works that I was thinking about when I wrote this slide. And so I'm sort of where I wanted to be now, and I can take questions. If you want questions, there should be a guy with a microphone about there. So whoever has, yep, he's there. So if you want to ask a question, please come up and get the microphone so that everybody can hear what you say.
Does it work? Yeah. I wonder how did you get in touch with the Simula? You have mentioned that several times that you was inspired by Simula.
Sure. I learned object-oriented programming from Christian Nygaard, and I wrote Simula in '71, and a lot of it in about '75, '76. So I think I held the record for breaking the Simula compiler for a couple of years. So I know it reasonably well.
Okay. But did it have anything to do with that Christian Nygaard was Norwegian and you were Danish? Or?
Oh yes, I had two sources of Simula. No, three. The first one didn't work, which was the academic papers. They were unreadable in my opinion. Until you understand what Simula is and what object-oriented programming is, you can't read the academic papers. However, I can read Norwegian. And so I could read the non-academic notes that they wrote for very new programmers. And that helped a lot. It was much clearer than the academic stuff. And then finally, Christian Nygaard for a couple of years came to Aarhus once a month. And my office was down at the base of the stairs leading up to the visitor apartment. And so got into a habit where Christian comes in. I mean, in case you didn't get it, Christian Nygaard is the father of object-oriented programming and Simula, together with Ole Johan Dahl. So he comes up there and basically sticks his head into my office and says, round up the usual suspects. Or something equivalent. And so he goes up to the office, I round up some students and some beer, and then we talk object-oriented programming for another 2 hours. And that's where I learned a lot. So yes, I appreciate Simula a lot. It just didn't run very fast. I wouldn't write a device driver in it. But that wasn't what it was for. So it's a fair critique that nobody should object to.
Okay, you mentioned macros. What other feature, if removed tomorrow, would be unthinkable, but you could see deprecated or removed in 10 years?
The preprocessor.
Oh, yeah, macros on preprocessor.
All of it.
Yeah, sure, but what else?
Oh, other things are less easy because they are not as easily isolated. There are things that cause a lot of trouble, but I have little hope in changing. I mean, the C declarator syntax, even Dennis thought was a mistake. But he couldn't do anything about it. Neither do I think I can. The fact that you can convert implicitly both ways among built-in types, from char to double and back and things like that, is things I would like to eliminate, but I'm not sure I can. I am trying. If you use the guidelines and use the guideline checker, it will not like you converting a double to a char, and it will statically tell you don't do it. So that is a step on the way. On the other hand, major features, I think for every major feature, I or others made some mistakes in the realization of the ideal. And we can think about simplifying and changing the details, but you can't take anything major away because it'll break maybe 1 million lines of code, and you don't know what code that is easily. I think we need better tools for static analysis and for code transformation to help us to bring up the code. But I'm less optimistic about outright banning things. If somebody proves me wrong here, I'll be very happy. But first, I want to do with checkers and analysis to bring people along.
So, in your book on C++11, amongst many other things, one of the things you talked about is exceptions. The impression I got from this, and I hope it's a fair one, is that you consider the field of exceptions and exception handling to be relatively immature. And I wanted to ask if you have any insights as to where you think, or how you think this field might develop in the future.
I actually think C++ exceptions, now we've gotten rid of exception specifications, is quite good. I also think that the implementations leave a lot to be desired. So people back in the early, when were they first doing it? Late 90s, early 90s, was very nervous. And so they were implementing things that wasn't really good for high performance, like walking the stack twice just to get debug information. That should not happen in production code. So I think what we should do to get good exception handling is actually better implementations, which for reasons of backwards compatibility is going to be a real pain and may not happen, and then some more systematic and well thought out use of no except. I mean, if you know that no exception can be thrown, you can say so. And that helps a bit. But I think we are for a while stuck with 1990s nervous implementations. That is, when people implement something that's brand new, they tend to leave in flexibilities, and if they've done that, they may need binary compatibility forever after and get their slow implementations. I am not recommending anything further than that. For instance, I think it's correct that we do not do detailed compile time analysis or declaration of what can be thrown and things like that.
Hi. Right now, the technologies for heterogeneous programming, like CUDA, more closely resemble C code, or at least a subset of C++. You state that supporting modern hardware is one of your goals for the language. Could you elaborate how you see that? Sure.
Fortunately, CUDA and the other guys and some of the FPGA guys are doing better integration with modern C++, so it's coming. Part of it is to get hardware to improve, like uniform address spaces for GPUs, so that you don't have to do explicit copying. But they're also experimenting with abstractions. The problem is, if you write C-level code, you get a whole bunch of pointers, and pointers poison the optimizer in many cases. And I think people are learning how to use the symbol abstraction facilities, the Constexper facilities, and I'm sure we could do much better. We have people like NVIDIA and Intel on the committee, so we are looking into that. We'll see where it goes. It's on my list. It's not what I personally do most of. I keep an eye on it because I need it for work. But you could get a better talk on that by some of the people in the concurrency group or in the games and financial and whatever group, the SG14.
Thank you.
Hello. I actually have two questions. One is very small, another one might be a little bigger. So this very small one is regarding the clear goals that we set up as a C++ community, and I'm wondering, does the committee have any idea currently? Is it gonna be C++ 19 or 20?
I would put my bet on 20. We delivered in 14. We will deliver in 17. People thought we, and especially me, was insane about 14. After all, we just spent 12 years doing a 10-year project. We delivered on time, and the implementations caught up. We are doing the same with 17. I'll put my bets on, I'll put good money on 20.
I see. And the second question is regarding, so you talked just now about the problems of implicit casting between built-in types. And if I remember correctly, there was a proposal from Walter Brown about strong type defs or opaque type defs, and I was wondering, what did you think about that? I think it was dismissed.
There has been problems of strong type defs forever. When I first joined Bell Labs in 79, Dennis was trying to figure it out. And there's been 4 or 5 proposals since that for strong type def, and they have all floundered on the point is that if you just want a strong type def where the thing is homogeneous, that is, you take 2 T's and you produce a T. If that's all you want, it's easy to do, and you can actually do it without a language extension. Whenever people start talking about language extensions, they start suffering feature creep. You would like to have a constructor, for instance, so that if you try to take arguments that are not T's, but could be easily converted to T's, you would like to be able to do that. And you would like to prevent implicit conversions of implicit narrowing conversions. And then you want the result type sometimes not to be a T. Like if you multiply 2 integers, it would be nice to get along or something. And so these proposals tend to run into complexities. What if you would like to have user-defined constants, so that you have seconds and milliseconds, and you would like conversions not to happen? So I'm not optimistic, and I'm not in favor of these proposals. If you want your form of strong type defs, define a class. Classes are more efficient. It's no longer the case that if you'd have a class, you immediately shed the registers into memory, which you can't afford. It doesn't happen anymore. So you can write a nice little class that does your version. And maybe eventually we should get a standard library version of the most common things, but I'm not in favor of a language extension for strong type defs because I've seen it fail too many times since 79.
Thank you.
Hello, I have a simple question about exceptions. Is the throwing exceptions inside destructor have it any real useful scenario, or this is a pure evil?
You can throw exceptions inside destructors, and it's very useful. You just mustn't let that exception escape.
Yes, I mean exactly.
Yes, I thought that's what you meant, but there's, what is there, 700 people here? I just wanted to make sure that people were aware of the distinction. And I mean, I have production code that throws inside a destructor. We just make great care of catching it. And we don't want those to escape, because we don't know in general how to handle throwing destructors. There's just too much code that breaks there, and people usually come up with arguments that my particular case doesn't have a bug in it, and they're usually wrong. So what we do instead, if you cannot close an object, say close a TCP connection, what you do is you convert the exception into an error list somewhere that's processed separately. So the object closes down, it leaks the resource. It's almost always a resource you can't give back. It leaks the resource to a leaked resource list. So it's not really leaked. And then you work your way through that list sometime where it's convenient to your application.
Yes, but is the possibility for exception to leave destructor and goes away, is it valuable enough to preserve it in a future versions on C++?
I would not be sad if we banned exceptions from leaving destructors. The question is, what would that mean? Currently it's undefined behavior. I would rather not have every destructor decorated with runtime checking code against exceptions, because then every destructor could be slower and we would slow down the whole program. I'm reasonably happy with it as it is now. If you could find a zero overhead way of banning the escape of exceptions, I would take it, but I don't know of one. There's a cost to that guarantee. So what do you actually do if you catch an exception that's trying to get out? Throw an exception? No.
Hi, Bjarne.
Hi.
Scott Myers retired from C++ about a year ago. Do we need to be worried about you?
I mean, thank you for being potentially worried. There's a difference. Scott has a consultancy business, and Scott retired, so there's a consultancy business less. I have worked on the core of C++ and on its standard libraries for a lot of years. C++ is coming up on its 4th year's anniversary at the same time as C++ 20 should come out. And I think if I left, it might be a different thing. I actually work on the language definition, and I don't have any plans of retiring. I have tried to get out of C++ standardization and implementation several times quite seriously over the years, and I've failed. So I'm probably not good at it.
Hi. So I have a question in the context of the last code example, combining structured bindings, modules, and concepts. After C++ 17 comes out, do you plan any books which would give advice on how to effectively design APIs combining those features? And I'm thinking not only of the C++ 17 standard, but potentially also the technical specification and concepts and modules, how to combine those features effectively to have a good, usable, maintainable APIs.
I think that concept should have been 17, and I think that modules couldn't quite have made it, but they're so close that I would think they should go in very soon. I think that we should vote them into the language, say, next year. That would give us 3 years to find any problems and fix them, in the idea of integrating early. And structured bindings are already in. So I think this can, and I'll be very disappointed if it won't happen. The bigger question is if we could agree on a set of general principles, like the ones I was working with from the early days, articulated in '94 and such. And I find that a lot of people don't agree on fundamentals like that. A lot of them have never seen these things. We have people in the Standards Committee which I'm pretty sure has not read DNE. I wouldn't say they weren't born when it was written, but it was an antique. They don't quite see the relevance. So I think that getting agreement of an overall guidance, design principles, direction, getting people to agree that we need to get something finished instead of having, like we had for 17, I think we have something like at least 6 or 7 major extensions that would have made a major difference to people if they had come, that was almost ready. That's bad management. When I was at Bell Labs, one of the rules was that something significant came out of a department every year. And it was not good to have 6 things that was almost ready. That was a sign that you haven't made up your mind of what you were doing and which business you were in, and you would probably be out of business very soon. And that kind of thing worries me. But people have a real hard time of deciding on priorities, on what comes next, what should be not have priority is the hard thing. Everybody wants everything, but how do we decide what we do? And we don't want to get into the situation where we have to wait 12 years for the next major thing because everybody wants everything. And it's a really hard thing because it's not language technical. It's not what you learn in computer science 101, engineering 101. It's not what you, some of us learns it in industry that you must deliver, but getting agreement on these semi-philosophical things is very, very hard, and I don't know if it can be done. So I have hopes for 20 for concepts, modules, and contracts, and I hope they don't get mauled too much in the standard process. Simplicity is a feature, but simplicity is a feature that a large group of people find it hard to achieve. So, okay, I've said my concerns. It's not going to be easy, but, we have a pretty good track record.
Thank you. And just one question. After the C++ 17 standard and after C++ 20, do you plan any new editions of your books, including these standards?
I am not sure about the books just now. I'm pretty sure I will not do a 5th edition for 17. I don't think the changes are major enough for that. And similarly, the Swan book, the undergraduate textbook, I don't think it is major enough for that. I might do an appendix or something and put it on the web. I'm tempted to work on a tour of C++, the overview, making that 200 pages instead of 180 pages. I'm excluding the index and such, if you really count. I think I could make a contribution. And one of the contributions of the tour, which I think is an underrated and underused book, is it's selective. It actually is a value judgment. You have this 1,400 or 1,600 page document, and how do you get a grasp what's there in a weekend or in one flight across the continent? You can do that with a tour, and I think more people should do it. And I think that choosing carefully among 14 and 17 features, I could do it in maybe 20 pages. I don't want to bloat. The problem with a lot of traditional C++ books is they are trying to teach everything to everybody. And that is not the aim of the tour.
Thank you very much.
Hello, thank you for your talk. I have like a short question. It's about uniform initialization and normal initialization. You probably know this problem like with when you initialize vector of ints, when you use like normal initialization and uniform initialization, you get a different results. So what do you think about this? Because like now it seems like...
Sorry, could you give a concrete example so that I'm sure I understand?
It's like, yeah, when you initialize vector of int with two ints, when you use classical initialization, it's like a size and element.
Yeah.
That will be
Okay, fine. I was just trying to make
sure.
sure.
So this one, yeah. And I mean, like, what do you think about this? Because like we have now two ways to initialize objects, and we have to use like in one context one, in other context two. So we got kind of like, yeah.
Yes. Okay. Now, if I'm going to design vector today, I would have a let's call it a range type. And so if you could not have an integer and an integer, that would be two integers, and it would be two integers with their values. If you wanted to do the initialization either with parens or with curlies, you would have to say range 10. Now, I can't do that. We might, I mean, in my own code, I can do something like that, but for the standard integer, vector, I can't. So I'm using the convention that you use round brackets if you are not giving a set of elements, and you use curlies when you use a set of elements. You need somewhere to distinguish. It can either be in the type, like what I wanted a range type to, when you wanted to say a range, not just 7, but range 7, extent 7, whatever you want to call it. And not doing that, I use the syntax. And that's an imperfection. You have an old language. For initialization, there's a history going back to 72. And sometimes you get a compromise. I would really like to write my code using nothing but curly initialization. But I can't get that for things that has been standardized, well, almost 20 years ago.
Thank you.
Hi, thank you for your talk. I got curious, what other programming languages are you using today, and what features could inspire you for C++ from them?
I always dodge that question somehow. Because, you know, if I say something good, it gets blown up that Bjarne prefers this language.
Okay.
Or if I say something bad, Bjarne has been rude. And so I experiment with a variety of languages. For my sort of production work and most serious work, I stick to C++. But I guess I knew maybe 25 languages when I started, and I know many more now. And I have learned new ones in the last couple of years. But for real work, I stick mostly to C++, and I would like not to answer the specific question.
That's okay.
Hi.
Hi.
I think I remember you working on the uniform call proposals, and I haven't seen that anywhere in the talk and in the future directions and stuff. Can you give us an update on that?
Sure. It's a wonderful proposal, and the committee didn't like it. I think I'm right about it wonderful, and I think the committee was wrong about it being dangerous and destroying interfaces and such. The reason I want it is that we have a problem when we write a library about what kind of types can it take. Should it be types that you can call with the object-oriented syntax, or types you can call with the functional syntax? And this leads to libraries that either has twice as many operations as they should, or more typically a lot of extra functions and converting functions and such. So you have the old reference wrappers and not reference wrappers. These little wrapper things for turning conversions into the right syntax. For STL, the right syntax is f of x, not x.f. So any object-oriented code that wants to use the standard library has to use a wrapper. We also see a proliferation of duplicate functions. So remember begins versus freestanding begins, and we see standard library support for those conversions and such. And I think it's a terrible mess. It complicates library writing, it complicates library use, and we should do it. I have a proposal. The last proposal has no breakage of old code, and well, people say that if you rely on overloading for resolving these things, you get serious problems with maintainability. That's their opinion, it's not my opinion. And I got voted down.
Oh.
It happens.
Yeah, I was a bit worried with all the begin, C, and data size free functions that were added just to handle ranges, and the C-style arrays the same.
Yeah.
But, thanks.
Yeah. We can't get everything we want, you know.
Hello. I have a kind of a philosophical question. For 16 years I'm writing C++. I hear about C++ dying, but I'm pretty sure I'm safe for another 16 years with C++. However, do you see a time when C++ and other languages will become obsolete due to computer systems being able to understand our intent good enough?
I mean, obviously, we would like to have something that's radically better than what we are doing today. And I'm an optimist, so I think we'll get there. I mean, there's about 1 million years till the sun goes nova, so we'll get there, I'm sure. Whether it's in my lifetime, I don't know. I was once asked a sort of silly question in a panel. In 50 years, will all programming be done by robots? And people tried various answers. I scratched my head and says, yeah, but which language do you use for programming the robots? And so it's a philosophical question, it's a waffly answer, but I don't see the end of C++ or any other major languages any day soon. About 1990, John Carolan from one of the first companies that was shipping C++ gave a talk that about C++ in 25 years, and most of us were shaking our heads. That was a bit optimistic. We're still here, and we're growing.
All right, thank you.
I think we're getting a timing warning. Is that correct, Jens? Or we'll just wait?
I think we have 5 minutes.
5 minutes, okay, we're not out yet. He was just waving his little drone around, so I thought maybe it was an indicator.
The word abstraction was one of the keywords in your presentation. What do you think about the modeling languages in the future? How will fit with the C++? Will be concurrence?
A lot of so-called modern languages have borrowed a lot from C++. C++ borrows ideas from other languages, usually with acknowledgements. And I think if other languages were as gracious with their acknowledgement as I try to be, C++'s reputation would be higher. On the other hand, in many areas, C++ is more modern than the so-called modern languages. Just look at the things we can do at compile time. Just look at the flexibility of the type system. We're not doing badly. Sorry for holding my hand up there, but I have the lights in my eyes, and if I don't do this, I can't see you.
That's fine, don't worry. Thank you for talking. I've been writing, I think I first wrote C++ in 1986, and since then I've worked in quite a few coding jobs, but nowhere have I worked where anyone has switched on RTTI. I wondered if that was an oversight on their part, or if you had any good use cases for RTTI.
RTTI is very badly implemented in a lot of places. And that's same kind of problem as we have with exceptions. But I can assure you that there's hundreds of thousands of people using it. So it is necessary. You can't just throw it away. What I would like would be an improved implementation so that you did, some of them doesn't look anywhere near optimal. In particular, some goes through a complicated song and dance in cases where a simple solution would do. I once, for use in embedded systems, designed a system together with a guy called Tom Gibbs that did RTTI, did dynamic casts in short constant time, provided you didn't have too large a hierarchy. And so it is definitely possible to get the cost down to compare well with a function call. But people haven't done it.
Okay, the last guy.
Hey, thank you for being here and for staying around. And my question would be, what would you give as a suggestion to a 20-year-old Bjarne with the knowledge you have today?
Oh, this is the time machine question. I sometimes bring it up myself because I'm pretty sure I'm not smarter than the 1980s vintage Bjarne. I just have a little bit more experience. He also knew more about what was available and feasible at the time. Remember, at that time, machines with 1 megabyte of memory was a dream. And to begin with, I didn't dare dream that much, but then I got over that problem. And 1 megahertz was a fast computer. You could dream about that. And I overshot the target. That's how C++ could run on PCs, the original ones. So it's not just that I would like it. Saying that I want a cleaned up version of C++ 17 with concepts and modules, of course, in 80, it's just ridiculous. Anybody could say that, but they couldn't implement it. If they could implement it, they couldn't teach people how to use it. So with those caveats, I could think about breaking C compatibility for the declarator syntax, but C++ would have been stillborn. So what could I actually have done at which time? And so if I'd had that time machine, and if I'd gone back to about 86, and told that vintage Bjarne how to do concepts right, I think I could have done it. Because I was trying at the time. There was 3 things I wanted. I wanted full flexibility, 0 overhead, and good interfaces. Remember, I was the one that put function prototypes into C. It's not a new ideal. So I tried hard to do that. And as best I know, nobody knew how to do all 3. And I picked the 2 necessary ones, generality and performance. If somebody has shown the concepts as we have them proposed today, they would have been simpler to do without having the current templates. And I think they would have been easier to implement than the current templates. So I think if you could have whispered in my ear in 86, we would have had better templates for the last 20 years. So I think that's a straight answer. It would have been feasible. But you first need to invent that time machine. Okay, thank you.
So